a fair amount of information that may not be in every spreadsheet export that you'll see. So I think it's really important to have the RCC files, and also if you'd like to do advanced analysis, which has can be pretty powerful, you definitely need the RCC files for that. And in addition, if you want to do the advanced analysis, you would need to import the RLF file. And the RLF is actually the file that was used when the scanner matched the barcodes on the cartridges to the targets of interest. So that file also contains some annotation information that's important for advanced analysis. But let's just focus on the basic advanced analysis now. So, this is what NSolver looks like when you open the window. Basically, up here in this raw data panel, you'll see this is just a list of RLF names. So RLF is the file, again, that associates a barcode with the target. So every experiment you do has an RLF that is used for the scan. And when you import data, raw data, the RCC files into NSolver, it'll just associate it with an RLF. Even if you don't import the RLF, because the RLF name is in the RCC files, it'll take that name and organize it according to the RLF. So,
So wait a second. When you say, can I interrupt? So.
Oh no, it's okay. You can interrupt. I just asked you to repeat that because I didn't quite hear the question.
So when you get the RCC file from the machine, the IL file is already associated, or you have to import twice?
Yeah. The RLF, yes and no. So the RLF is needed for the scan. So you need to both upload the RLF to the digital analyzer, and if you'd like to do an advanced analysis, you need to also import it into the NSolver program. Does that make sense?
So you already have the RLF file.
Because you import that into the scan already.
Yes, and if you're ever, we work with a lot of customers who receive the data and do the analysis, but they actually weren't involved with running the assay. So if you find yourself in need of an RLF, we have them all here. So just reach out to support at Nanosteing, say I need this RLF, and it's easy, very easy for us to send it to you. So, but for basic analysis, the RLF is not needed.
Okay.
So I'm gonna find
all the genes over here.
Yeah. Okay.
So those are the 12 samples.
I'm sorry?
Those are the 12 samples that I just sent it to you.
Yes, those are the 12 samples. Yep. And it'll just look it'll look in an unzipped folder for all of the RCCs. And if there's a problem, if it's already been imported into NSolver, it'll give you an error message. But I'm just going to say next. And this is kind of an important window. You don't have to actually do anything here, but it's kind of important to understand what's going on. There are two points in NSolver basic analysis where there's some QC metrics applied. And the first one is actually when you import the files. And what it's doing here is it's looking for any systemic problems. This is sort of independent of the sample quality, data quality. It's looking at the imaging quality.
Okay.
How many fields of view are registered. It's looking at the binding density, and this is can be a bit confusing to customers. Binding density is basically the number of fluorescent spots per square micron on the cartridge. And sometimes customers will get a high binding density flag. And I say, as long as there's no imaging flag, your data's fine. If binding density gets too high, you may lose imaging quality, but if your imaging is good, then there's nothing really to worry about there.
So those numbers are usually
also,
so those numbers are usually the default, right?
Yeah, they're default, and
Okay.
I think there's no reason to change the default as
Okay.
long as you understand what it means. There are some customers who apply their own QC values, QC metrics, at which point feel free to manipulate these, but I usually recommend keeping them as the default value.
Okay.
Yeah, so this one here is positive control linearity, and you'll see, I don't know if you took a look at the Excel file, and we can look at the raw data again, but the positive controls are basically a fourfold dilution of each other. So it looks at the linearity of the positive controls. The linearity issue can mean a lot of different things, including, a problem with the hybridization itself. So that's one metric. And there's also the limit of detection, which looks at the 0.5 centimole. It looks at one of the lower positive controls, and it's making sure that it's greater than 2 standard deviations above the mean of the negative control. So my quick way of explaining this one is it's just making sure that the positive controls are robust compared to the negative controls. So this can be flagged for a couple of reasons. If for some reason your positive controls are low, or sometimes I've seen this flag when there's a problem and there's a lot of background and your negative controls are particularly high. So that's just a brief rundown. And all this information's in the NSolver manual if you need to refer back to it. So I'm going to import this here. Okay. So now I'm going to look for, here it is, mouse immunology. And if you scroll this way, all right. So you have one flag here. And window there, I'm not sure why. You have one flag. So we can export the raw data and see what happened there. This is a 0.5 centimolar detection flag. So let's export the data. So I like to first import it into NSolver, and then I export it because I think it's good practice to look at the raw data to just do an assessment before you go forward with analysis. So I'm going to export. I personally like the RCC tool, collector tool format when I export because it has some of the imaging metrics. So I'm going to do that. I'm going to put it on run on the desktop. All right, so let's take a look, and this is probably very similar to the
Excel sheet.
what you were looking at before. So which is, let's see, this actually looks okay. So it looks like is that lane 8? Yeah, lane 8 was the one that was flagged. So I'm going to just highlight it so we can take a look.
So the whole sample is flagged?
One thing, well, it's flagged. I can tell you why it was flagged. It was flagged because the positive controls are a little low there.
Okay.
But honestly, eyeballing this data, I see a lot of data sets. This looks nice and robust.
Okay.
Actually, the endogenous counts look quite good here, and you're seeing quite a nice. A couple things I want to point out. The background, first of all, is nice and low here.
Okay.
The highest background count is 24, which is it's very nice. This is what we want to see as far as background. And as far as the endogenous counts go, you see a nice range. You see your certain ones are expressing at background, and others are expressing quite robustly. In fact, you have some quite. This is a large code set. So you're going to see.
Yeah.
Not every sample is going to express, and some examples are going to express very highly,
Yeah.
But this looks nice. This is actually a nice data set here.
So maybe the 5,000 is the
like,
cutoff or whatever for the positive control?
24,
Yeah, it looks like, and I'm going to tell you why I think that these positive controls are a little low. You'll also see they're a bit low for these samples. It may have to do with the binding density.
Okay.
Your binding density, it's not high enough to trigger a binding density flag, but sometimes you'll see some binding density variation, or rather some positive control suppression when your binding density is high, and that's only because when you set up the assay, the positive control targets, they live in the reporter probe tube. So the positive control targets are added at the same concentration to every hybridization reaction. So if you have a sample that has, or rather a hybridization reaction that has a higher sample input, there's going to be competition on the cartridge between the positive control target probe complexes and the sample target probe complexes, if that makes sense. So it's basically, when your sample input is high, you may see slightly lower positive controls. If your endogenous counts look nice and robust, there's nothing to worry about. It just means there's a lot of sample in there. There's a lot of data. This data set looks good. This is a good data set. So,
okay.
So how high is high for the binding density?
I'm sorry?
How high is high for binding density?
That's a good question. So it'll get flagged when it's over 2.25. However, I've seen binding density go to 3, and it can be okay. It's a little difficult to say, what exactly is. There's no strict cutoff. It really depends. You don't want it to get too high. You don't want it to get much higher than this. This is actually a pretty nice range. Once you start getting above 2, you get into that zone where, okay, my binding density, my endogenous counts are really robust. I'm seeing a lot of data. Eventually, you're going to hit saturation, and see how it says FOV count versus FOV counted?
Yeah.
FOV count is what we set, the number of fields of view we tell the instrument, the scanner, to count. FOV counted is how many fields of view it's actually able to count. So this FOV counted number will become low if there's an imaging issue, if the cartridge isn't seated properly in the scanner, if there's some debris or something on the bottom of the cartridge that's causing it to not be able to focus, if there's external vibration. We've seen cases where, sometimes there's a big centrifuge on the same table as a nanostring, and that, that can affect the imaging quality.